Hello and welcome to the Abingdon Physics YouTube channel. Today we're going to be looking at Edexcel IGCSE Physics Topic 3 Waves, in particular the properties of waves. So here is our spec points. We have spec point 3.2 all the way to 3.9. Abingdon pupils, spec point 3.8, the Doppler effect will not be on your waves test coming up. So when I get to that bit of the video, please just skip forward. So spec point 3.2 says to explain the difference between longitudinal and transverse waves. So let's start with longitudinal waves. Longitudinal waves oscillate parallel to the direction of energy transfer. And those are the words that we need to use. This is often a 2-mark question in an exam to explain what a longitudinal wave is. And it is a wave with oscillations parallel to the direction of energy transfer. This can be shown by the image in front of us, and we must use that word oscillations. An example of a longitudinal wave is sound or ultrasound. Moving on to transverse waves, these are waves with oscillations perpendicular to the direction of energy transfer. An example of a transverse wave would be light or any other EM spectrum wave like radio waves or microwaves. Again, it is really important we use the word oscillations and perpendicular in our answer. Okay, now we move on to spec point 2.3, know the definitions of amplitude, wavefront, frequency, wavelength, and period of a wave. Wavefront I'm going to leave out of this spec point, and I'm going to do it when I talk about the Doppler spec point later. So let's look at amplitude first. Amplitude is the distance between the mean position to the peak of the wave. So the amplitude would be from here to here, as shown by the drawing that I am labelling now. Now, one wavelength is the total distance from peak to peak of a wave. So that would look like here on my wave. A wavelength could also be done from trough to trough. It's really important that our x-axis has distance on it when we're doing the wavelength. The time period is similar to the wavelength, however, it is for time. So it's the time taken between peak to peak of a wave, and that can be shown here on our drawing. And finally, we have frequency, which is the number of full wave cycles in a second, and it is measured in hertz. So we move on to spec point 3.4, and this is the most crucial and important part of waves. It is the idea that they are transferring energy without transferring matter. So I'm going to repeat that bit. They transfer energy without transferring matter. And that is the crucial idea and whole concept of waves. Now we move on to spec point 3.5, and this is the wave equation, where we have wave speed equals frequency times wavelength. Wave speed is the speed of the wave, and it is measured in meters per second. Frequency is how many waves there are per second, and it is measured in hertz. And wavelength is that distance from peak to peak of the wave, and it is measured in meters. When we use this equation, we should always make sure we are writing out the equation, then the sum, then the answer, and then the unit, showing all of our working, as this is regularly a 3-mark answer question. Now we move on to spec point 3.6 to use the relationship between frequency and time period, where we know that frequency equals 1 over time period. We remember that time period is the time it takes for one full wave, and the frequency is the number of waves per second. So if I had a time period of, say, 0.25 seconds, that means I will have a frequency of 4 hertz, because there are 0.25 seconds for each wave, and I can fit 4 of those waves in each second. Therefore, my frequency would be 4 hertz, or 4 waves a second. Spec point 3.7 is simply to use these waves in different contexts, which means being able to answer different questions where they appear. And this is for all EM waves and all different sound waves. It's not going to change the equations we're using, so it should not affect us how we use these equations. Okay, spec point 3.8 is about the Doppler effect. So if you're an Abingdon 4th year, you can skip this slide as it does not affect you and we haven't done it yet. But let's talk about the Doppler effect. And to do the Doppler effect, first we need to know what a wavefront is. A wavefront is like a surface where all of the waves are at the same point. So the way I like to imagine this is if I dropped a pebble in the ocean, as I can see from this drawing here, I've got that as a top-down view, and you can see the ripples going out. Now, all of these ripples are going to have peaks where the blue lines are. So it will look something like this. So these big blue circles represent a peak of a wave transferring outwards. And so that means that the distance between these points is a peak to peak, and therefore this distance here is a wavelength. So the Doppler effect explains how the frequency and the wavelength of a wave changes depending on the motion of another object. So let's start by looking at this car here moving away from the person at A. Now we can see the blue lines I've drawn to represent the wave fronts are being bunched up in front of the car, and they are being stretched out behind the car. So where observer A is, the wave fronts look further apart. This results in the wavelength that observer A sees and hears being larger than it would be normally. Now the wave speed of the waves is not changing. So we have our equation V equals lambda F. And if for the observer A, lambda is increasing, this must mean that the frequency is decreasing. And if the frequency is decreasing, therefore the person at A will hear a lower pitch as something travels away from them. And the vice versa happens exactly the same with the opposite direction. So if the object was coming towards A, the wavelengths would be condensed and smaller, therefore the wave speed would be the same and the frequency would have to increase and the person would hear a higher pitch. And this is why when you're at an F1 stadium, or if you've heard that classic race car sound going of like, it goes from high to low as it passes us, and that is due to the Doppler effect. And our final spec point for this is to explain that all waves can be reflected and refracted, and I will go into that in much more detail in the light section of the waves topic. But yes, all waves can be reflected and refracted. So let's move on to some questions for this topic. And the first is, which arrow represents the amplitude of this wave? And so we should have ds. Which arrow represents the wavelength of this wave? We notice it is distance on the x-axis, so we should be seeing a wavelength, and it's the distance from peak to peak, which is q, so b here. And which type of wave is this water wave? Water, we should know, is a transverse wave. Next up, we have sound travels as a wave. So a buzzer produces a sound wave of frequency 2.9 kilohertz and wavelength of 12 centimeters. State the equation relating wave speed, frequency, and wavelength. Well, we have our equation of V equals lambda F, where lambda is that wavelength that we mentioned earlier. So calculate the speed of the wave. Well, to do this, we first need to make sure we are transferring frequency into hertz and we're turning wavelength into centimeters. So frequency should be 2,900 hertz and wavelength should be equal to 0.12 meters. And when we do our maths, we remember we write equation, sum, answer, unit. So we write out our equation again of V equals lambda F, which is equal to 0.12 times 2,900, which equals 348 meters per second. So we can fill that in there, and that is our full marks for that question. So here is our next question, and we are asked about different types of waves. We have the surface of water having transverse waves and sound waves being longitudinal waves. Describe the difference between transverse waves and longitudinal waves. So the key difference is that transverse waves have oscillations perpendicular to the direction of energy transfer, whereas longitudinal waves have oscillations parallel to the direction of energy transfer. And it's really, really crucial that we're using the word oscillations in our answer, parallel and perpendicular in our answer, and energy transfer in our answer. And if we check the mark scheme, we see the same thing, saying transverse waves have oscillations perpendicular to the direction of travel of the wave. Direction of travel of the wave and direction of energy transfer can be used interchangeably as well. Similarly, oscillations and vibrations can be used interchangeably, and you will always get the marks for either of them. And we have longitudinal waves have oscillations in the same direction as the direction of travel of the wave. The same direction as direction of travel of the wave is the same as saying parallel. I, however, would always advise saying parallel rather than same direction. I think parallel sounds better. And now we move on to our Doppler effect question. So if you're in Abingdon 4th year, this question doesn't relate to you and you can be done with this video as this is the last question. We have a car travelling in a straight line along a road and the car passes by a person on the road. Before passing the person, the driver of the car presses his horn and the horn makes a loud sound of a consistent frequency. And the horn continues to make a sound after the car has passed the person. Discuss the differences in the frequency of the sound heard by the driver of the car and the person at the side of the road. Well, let's start with the driver of the car because that's going to be the easiest. The driver of the car is going to hear a sound of consistent frequency. This is because the driver is moving alongside the car at the exact same rate, so there's no relative motion, and therefore the frequency will be consistent because the wavelength will be consistent. However, the person at the side of the road is going to hear a different frequency due to the Doppler effect. As the car approaches, there is a smaller relative wavelength because of those wave fronts being compressed. Therefore, because the wave speed of these waves from the horn is not changing, therefore the frequency will be higher as the car approaches. So they'll hear a higher pitch sound. As the car goes past the person, however, the wavelengths will become larger as their wave fronts spread out. Therefore, the frequency heard will be lower, and so the person will hear a lower pitched sound. And again, that is because the wave speed is constant, and we're thinking of our equation V equals lambda F. If wavelength goes up, frequency must go down, or vice versa. If wavelength goes down, frequency must go up in order for wave speed to be constant within that equation V equals lambda F. And if we check our mark scheme, this is exactly what we see. So the driver, we see a frequency that does not change due to no relative motion. Whereas for the person at the side of the road, there is nearly always a mark for saying Doppler effect. So I always highly recommend saying Doppler effect. So the frequency heard by the person at the side of the road is different from that heard by the driver. As the car approaches, the frequency is higher because wave fronts become closer together. Therefore, the wavelength is smaller. And then as the car moves away, the wave fronts become further apart, the wavelength increases, therefore the frequency decreases. And we need to mention that the speed of sound remains constant, and we are referencing the equation V equals lambda F when we are doing that. Thank you for watching this video. Please do subscribe and like. Please make sure you are watching this again before you have any kind of test on this topic, and make sure you are doing past paper questions, past paper questions, past paper questions. It is the best way to get these into your head. Thank you for watching again.